Assalamu alaikum everyone, welcome to a new video. In this video I will be going over the fundamentals and the beginnings of calculus. Basically we're gonna start calculus and I will try to explain the fundamental logic behind the formula of differentiation and integration. We'll start with differentiation rather than just focusing on rote memorization of the formula. So let's start. Basically, calculus aims to answer two very interesting questions in basically I wouldn't say math. It aims to answer two very interesting questions in life, but for now we'll just stick to the mathematical point of view. So the first question that it aims to answer is basically how to find the gradient of a curve. So right here, the gradient and the other question, which we will come to later in the later videos inshallah, is the how to find the area under a curve. So area under a curve. All right, for now we will be focusing our attention on the first question. So let us have a look at this. Let us assume that we have this set of coordinate axes, this x and y axis, and I draw a straight line. How will you find the gradient of this particular line? Obviously we have been doing this for a long time, since grade 7, 8. We know that to find the gradient of a straight line we use the formula m equals y2 minus y1 upon x2 minus x1, right? Sorry for that, x1, right? Where basically x1 comma y1 and x2 comma y2 are two points on this line. I'll just call this P1 and I'll call this P2, okay? So let's say this point over here is P1 point over here is P2. Okay, so what we actually do is we take the y coordinate of P2 and subtract from it the y coordinate of P1 and do the same thing with the x's and divide both. So what we end up getting is like a rise over run. So if I were to do this like this, this over here is y2 minus y1 This here is x2 minus x1. Alright, I know it's getting a little messy, but please, I'll try to be a bit more clear from now on. And basically I don't have the required tools for right now. Anyways, so this is how you would find, and how we all find the gradient of a straight line. Now we have a new problem. Showing x, y-axis and x-axis. Now let's say we have a curve instead of a line, and let's say that the formula for this curve is y equals to x squared. Alright, this is the graph of y equals to x squared. How would you go about finding the gradient of this curve? Now, the method that we have all learned up till now is to draw a tangent. Like, for example, now first of all, everyone must understand the fundamental difference between a curve and a straight line, and why we have to use different methods for both of them. The fundamental difference, the core difference that actually changes the method, is the fact that the gradient of a straight line is constant throughout. It does not change, so it does not matter whichever points you pick on the line, as long as they are on the line. You can pick any points, and when you take the difference of the y's divided by the difference of the x's of those 2 points, you'll get the gradient, and it will be constant for the entire line. For a curve, the gradient of the line varies from point to point. It is never constant. It is not a constant gradient for a curve, and that is where the main difference, and for now our current problem, lies. So the method that you learn to find the gradient of a point on a curve, because every single point on a curve has a different gradient. So if you wanted to find the gradient, let's say at this point, alright, what you would do up till now is to draw a tangent line like this, and then, because the gradient of a line is constant, you would take any 2 points on this curve, somewhere here and here, maybe, I don't know, and then you would find, using your normal y2 minus y1 upon x2 minus x1 formula. Now, this is a completely fine method. Well, not completely, but it's a fine method. But the limitation of this method is actually human error and inaccuracy. Basically, this method is inaccurate due to the inaccuracy of drawing the tangent. So you don't get an exact gradient. It actually depends on how nicely you draw your tangent and how accurate that is, and that is obviously subject to some human error. So to find a more definitive mathematical method, like a more calculation-based method, what we do is we take a different approach. I'm gonna draw this curve again so that we have a better idea. This is our curve. It's not a very good curve, but let's see if I can make this better. Okay, that'll do. This is still the graph of y equals to x squared. Okay? Now, let us think a little bit. First of all, we have all studied functions. We know that this y equals to x squared can be expressed as a function of x. Basically, y can be expressed as a function of x. So I'm just gonna rewrite this, no problems. Okay? That's our first thing. Secondly, let's think a little bit about this. Let's say I want to find the gradient of this curve at this point. It's more or less the same point as before. Okay? Hope you can all see this little point over here. Now instead of drawing the tangent, what I will do, I'll just pick another point on this curve a little further, somewhere maybe here. That's not on the curve. Yes, somewhere around here. Alright, I'll call this, let's say I call this point P. I'll call this point Q. Okay? And I'm gonna say that the coordinates of P are x. I'm just gonna call them x for now. Okay, now you have to pay attention. X and the corresponding y coordinate. But since I have said that y is equals to f of x, instead of y over here, I'm gonna write f of x. Is that clear? I hope that's clear to all of you. As for q, I'm gonna call this, the x coordinate of q, something different. I'll use a different notation basically. Let's actually extend this axis so that it's easier for us to see what's going on. Okay. Right. I'm going to call the x coordinate of q x plus h, where h is a small difference. Does this make sense? Hopefully it does. Basically, h is a small difference, a positive incremental difference that I add to x to come to the x coordinate of q. As for y, the y coordinate of q, simply because I have the curve as a function of x, I can simply replace the x with x plus h for the y coordinate of q. So I just wrote this. Hopefully this is making sense up till now. Now I'm gonna find the gradient of PQ. Okay. Wait a second. Oh, that. There we go. So basically I'm gonna find the gradient of PQ. I am not finding the gradient of the curve at one point. Basically I'm not even finding the gradient of the curve as far as it's concerned for now. I'm finding the gradient of this line PQ. Okay, now since this is a straight line, what I can do is just use the formula for a straight line, which is y2 minus y1 upon x2 minus x1. In this case, our y2 is the y-coordinate of q, which is f of x plus h. So I'm just going to write that over here. Minus y1, which is the y-coordinate of p, which is simply f of x. All upon x2, which is the x-coordinate of q, which is x plus h. I'm just going to put this in brackets so that you can see it more easily. Minus x1, which is the x-coordinate of p, which is just x. Alright, so we have some complicated expression over here. Let's simplify it. What is first of all, what is f of x plus h? Actually, we start from f of x because it's more easier to say. What will f of x be? Look, we already defined this as x squared. So what I can just do is I can write x squared in place of f of x. Now, we have all studied functions. We know that whatever is in the parenthesis in the argument of a function replaces all instances of that variable in the function. What I mean is, since right now in the argument of this function we have x, we simply had x squared. If I replace x with x plus h, I'm gonna get x plus h whole squared. As for the denominator, is simple, x and x cancel, and I'm simply gonna get h. Alright, we're nearly there. Now let's just simplify it a little bit. I'll call this x squared plus 2xh using the algebraic identity. Actually, I'll write it to hx and plus h squared minus x squared all upon h. We see that the x squares cancel out and we are left with 2hx plus h squared all upon h. We can see that we can factor out an h in the numerator, which will help us in this case, like this, and what we are left with is this. Now what I have over here, right at this step, is basically the gradient of line, whenever this PQ. This is not the gradient of the curve yet. Now let's see what we actually had over here. In our graph, look what actually happened over here. What actually happened was that, look, my motive was to find the gradient of the curve at P, but I didn't do that directly. I actually picked a point Q that was a bit further forward from the point P. And that bit further forward, I represented that as a plus h. Now, just think of this a little bit. If h was 0, could I find the curve of the could I find the gradient of the curve at P? What would actually happen if h was 0? If h was 0, then I would simply get x comma f of x as the coordinates for q, which are already the coordinates of p. So technically what I would end up getting would be the gradient at p. Now let's see if we can let h equal 0. In our expression, if I let h equal 0, do I get any infinities or any undefined values? No, I don't. So we are gonna write now the mathematical method of writing this. Now this is not actually strictly part of the CAIE A-level syllabus for mathematics, but you should know this because this concept is gonna come again in differential equations. So I'm gonna write this basically like this. And differential equation is basically in A2. In AS again, this concept will appear in a different part, which will be improper integrals, and we'll look at that time. Right now, I'm going to introduce you to a new thing. Whenever we have something like an expression like this, we have to let one variable go to 0 or any number. We use the concept of a limit. Basically right now, what is my motive over here? Is my motive to let x equal 0? No, it's to let h equal 0. So in order to let h equal 0, I will apply a limit on h. This is how it actually works. Actually, I'll label this extension for your reference, but I would really recommend learning this concept. It's useful in A-levels as well, and then you will go forward in your further studies, inshallah. It's a fundamental concept actually. So I'm actually gonna write this right. Wait a minute. Like this. I'm gonna say that the gradient of the line, actually the curve at P, I'm going to have to let h equals 0. I hope it makes sense why I have to let h equal 0. Basically, by the way, this is the notation for the limit I was talking about, and then we write our expression. Basically what this says is that the limit of 2x plus h as h approaches 0. This is what this says. I hope it makes sense. Why are we doing this? Actually, you know what? I'll show you on the graph what's actually happening as h equals 0. Actually, it's not equaling 0 technically, it's approaching 0. And I'll just show you. Let's come over here, and what I'll do is I'll copy this. Over here. Just this section. Move this over here. Actually, I shouldn't have done that. I have to copy this. Let's copy this and move this over here. Alright, now let me just show you what's happening as h equals 0. I'm seeing there's some parts of bottom straight. Okay. Alright. Now look. It's gonna get a little messy, but I hope it makes sense. Now, as h, basically h going to 0 means that h gets smaller. As h gets smaller, what will happen? What do you think will happen? This point is gonna go to the left. It's gonna go a bit more to the left and a bit more to the left. And it's gonna get closer to p. Basically, q is gonna get closer and closer to p as h goes to 0. So what will actually happen? Let's say h is 1, for example. And right now it's 1. And I'm gonna put it down and decrease it to 0.5, let's say. What's actually gonna happen that this new point is gonna be somewhere around here, right? So the line through p and q, because h is basically, you can think of h as a second variable that I'm just varying myself. And if h is equals to 0.5, it's still h, right? So it still represents q. So the new q, if h becomes smaller, will be somewhere around here, right? And we'll be going right somewhat around here. This and this. Is this making sense? What I'm saying is that this is your new q. I call this q naught. Okay, new q. And this will keep happening as h decreases in magnitude. This point is gonna get closer and closer and closer to p until it comes so close to p that it actually makes no difference at all. It's basically the same as p. This line, basically, I hope you're seeing that we're still applying the same tangent idea, but in a more mathematical and precise way. Like this, look. This is now even more closer to approximating the gradient of the curve at the point P. Pay close attention to my words. And this is gonna keep happening until h is like almost 0. Until it actually is 0. I hope you can see that as h becomes closer to 0, this becomes this line actually becomes like a perfect tangent at P. But it's like super accurate, much more accurate than you can draw usually. And so now look, I hope this made sense, like why I'm letting h equal 0. I hope it actually made visual sense. So now we're just gonna go to the mathematical part where we left off, and as I was saying, we're gonna let h equals 0. And what will it actually will do, I think it's pretty straightforward. You can see that the gradient of the curve at the point P is simply 2x. Now what this means is what actually matters. This actually means, now P is we actually picked P as a variable point, right? It was just x comma y, or x comma f of x. It wasn't a definitive point like 1 comma 2 or something like that. It was a point in terms of a variable, or in terms of two variables like x and y. It was a generic point anywhere on the curve. So what the gradient that we got from that is also a generic gradient for any point on the curve. which is like extremely amazing. It's beautiful. What you have in front of you over here, this 2x, what it actually says, it says that this 2x can give you the gradient of the curve y equals to x squared at any point on the curve. What you only have to do is plug in the x coordinate, just the x coordinate, not even the y coordinate, just the x coordinate of the point you want to find the gradient of the curve at. And this is actually necessary if you think about it. Like, obviously the gradient of a curve is different at every single point, as we discussed earlier. So the formula had to have something in it that explicitly showed that variation in gradients at different points. I hope it makes sense. So basically, let me give you an example. If I want to find the gradient of the curve y equals to x squared at, let's say, I'll just write this down actually. I'll write this down. I say gradient, for example, of y equals x squared at x equals 1. What you're gonna do, all you have to do is this. I'm just gonna say m. I'm still gonna just use m for now. We'll discuss the formal notation and the formula in the next class, inshallah. Right now I'm just giving you the idea about how we actually tend to approach these things, the logic behind this. I could simply have just given you the formula and asked you to memorize it, but it's much better to understand the concept, the underlying concept behind it all. So the gradient of the curve y equals to x squared at x equals 1 is simply 2, and in place of x I plug in 1, and here you get it, 2. Isn't this amazing? You just got the gradient of the curve y equals to x squared at x equals 1. You found the gradient of a curve without needing to explicitly draw a tangent. I hope this lesson made sense and you learned something new. Hopefully in the next class we'll start formally start this chapter about like the formal notation basically and the formula for this. And by the way, I forgot to tell this to you. Basically, this whole concept that we just discussed right now, I told you already that this was one of the questions that calculus aims to answer. But basically, this whole concept that we discussed right now is known as differentiation. Call this. Again, I'm gonna elaborate on this tomorrow in the next class in more detail, inshallah. But right now, I hope the idea makes sense, because this is the idea that we are essentially going to use in this whole chapter of differentiation. Alright, hopefully this makes sense. And so, goodbye, see you in the next class. Thank you.